All right, so we are in 5.1, and one of the things we are going to talk about is these things called radicals, which you kind of should have touched on in Algebra 1. At the beginning of my year, I showed my kids, but some of you weren't here, so I'm going to go back over this, how to deal with these things called square roots. And the way they teach them in Algebra 1, I personally do not like it. The way that they teach in Algebra 1 is they say, if I was going to do something called rationalizing the square root or simplifying it, they say, look at 50, and then they make a list. It goes 4, 9, 16, 4, 5, 25, count, 2, 3, 4, 5, 6, 7, 8, 9, 10, and this list would keep going. These are all the numbers that have what we call a perfect square. And so one of the things that they're using is that when you have a square root and you times by another square root, you can actually merge those together and put them underneath one square root. So meaning of this is if you have, and we'll use this later on, the square root of 2, say, times the square root of 3, you can make that just become the square root of 6 because they're both underneath radicals. You can actually multiply the 2 times the 3, which is 6, and so this simplifies to that. Well, if we can go this way in mathematics, we can go this way, meaning I can use that kind of opposite to deal with this guy. So what they do is they say, hey, look on this list and start with the biggest numbers first and see if any of these numbers can go into this one, which this number right here is the first one that goes into it evenly without, and so this would be my thing that I'm going to do. So I'm going to break this into really a square root of a 25 times the square root of 2. And then what you're supposed to realize is the square root of 25 is 5, and then you get 5 square roots of 2. That's the way they teach it in Algebra 1, which is all fine and dandy, except Algebra 2, we start talking about cube roots, and then fourth roots, and then fifth roots. Can anyone tell me why this way that they teach you kind of irks me and irritates me, and to be honest with you, I think it's stupid that they teach it like this. Why can anyone think of why this would be kind of a pain in the butt?
You might mess up with the numbers.
Okay. What are all these, Kelly?
Perfect squares.
Okay. What does this need? Can I use this list when I get to a cube root?
No.
What do I have to come up with?
Roots that are by the third power.
So I need a whole new list, and I need list of numbers. So my first number here would be 2 times 2 is 4 times 2 is 8. And then 3 times 3 is 9 times 3 is 27. And then 64. And then 125. I'd have to come up with a whole new list. Yes? Does that make sense?
Yeah.
And then guess what would happen when I had to go to the fourth power? Janina, would my list that I just created work for the next one?
No.
No, because all these have third roots, and the one that I'm going to deal with needs a fourth. So what would I have to do every freaking time I went to do these? I'd have to come up with the certain list. Well, what if I could show you a way that you don't need the list? And it doesn't matter what index, these are called index, which we're going to talk about today. It doesn't matter what index this is. So this is not referred to as a square root anymore. It is called a radical. The symbol is a radical. If there is nothing written here, it is understood to be a 2, so it'd be a square root. But this is technically a radical sign, and this is an index 3. So if there's nothing written, it's understood to be a 2. What if I could tell you, it doesn't matter. I don't care if you had the nth root. The way I'm going to teach you today will always work. I mean, to me, that's how I'd want to do it. So let's actually go back to the square root of 50, and let's deal with it. Well, the first thing you're supposed to learn is back in the day, you should have learned how to do a prime factorization tree. So you should know that you can break this down. And by the way, it doesn't matter necessarily how you break this down. You can break this down as to 5 times 10, or you could do it as 25 times 2. It works either way. But you're going to break it down, and when I circle is when something has a prime number. And so I can rewrite 50 instead of, I can write it as 2 times 5 squared. And then what I can do is I can use these facts. So I'm going to pause you there for a second. And what happens is we can rewrite this, technically if we wanted to, we could rewrite this as the square root of 2 times the square root of 5 squared. We're not going to do that every time. I'm just showing you this in the beginning, and then we're going to come up with a much faster way by the end of this. But what happens is you realize, hopefully, this doesn't cancel out because this is 2 to the first power, and you just have the square root, which doesn't cancel out, but the square root and the square cancel out. So my final answer is 5 square roots of 2. That's just the commutative property allowing me to switch the 5 to forward. So that would be that. So let's talk about this. What if I had, I'm going to do the prime factorization. What if I had 2 to the 5th power underneath this? So I'll just leave it as that. What in the world? Well, really, I could think of that as 2 squared times 2 squared times square root 2. If you think about it, that's because this is 2 2's. There's another 2, which is 4, and then there's another one, which is 5. So this right here is the same thing as that. Now, why am I breaking it up like that? So that I see every time I have a square under a square root, these two are canceling, leaving me with a 2. These two are canceling, leaving me with a 2. This does not cancel, leaves me with the square root of 2. And so my final answer is 2 times 4 is 4 square roots of 2. Now, the faster way to do this, instead of having to rewrite this out all the time, is to do this. You go 2. How many times can 2 go into 5? Because every time I make a pair, I get to pull one out. So you're saying, how many times does 2 go into 5? And the answer is 2 times. That's that 2 answer right there. Did you notice over here, you got 2 2's out? That's what this represents. 2 squared is representing the 2 2's that I got pulled out. But the problem is 2 goes into 5 2 times with 1 left over. And where's that 1 going to stay? It's going to stay inside that radical. So my final answer is 2 squared, which is 4 square roots of 2. I'm going to keep giving it to you in simplified version. So if I had, let's do 3. 2 to the, actually, I'll use different numbers. What if I had the square root of 7 to the 3rd times 11 to the 2nd power? Notice I've already done my tree factor. When I did my tree factor, I got 7, and then some number over here, and I got a 7, and I did some number, and I got 11, and I got 11. So these were my only numbers that were on my prime factor. So I broke this number down. Oh, there was another 7 in here somewhere. So I got 3 7s, or 7 to the 3rd, and I got 11 to the 2nd. Now, this is an imaginary 2. It's understood to be there. How many times does 2 go into 3? It goes into 3 1 time. So I get 1 7 out, but there's 1 left over. How many times does 2 go into 2? Goes into it 1 time. So I get 1 11 out, but this time there's none left over. And then I have the square root of 7 that's left inside. 7 times 11 is 77. So 7 square roots of 11 would be my simplified version of whatever this number was. This would be my final answer. Is this kind of making sense to anyone?
Yeah, it makes a lot of sense.
So the reason that this way is cool is because once I switch it to a cube root, the process doesn't change. You're still going to do your prime factorization for whatever you have over here. And when you rewrite your prime factorization, let's say it's 2 to the 4th times 3 to the third times 5 to the, let's go with big number, let's go to the 7th. Okay, how many times does 3 go into 4? That's what I'm asking, not the 2. It's not the 2. How many times does 3 go into 4?
1.
And so I'm going to get the base number of 2 out 1 time. Normally I would not write this one, but I'm doing that just to show you. So I get 1 2 out. But the problem is 3 goes into 4 1 time with what?
A remainder.
So I'm going to cross this out and put my little remainder 1 there. So I remember there's still 1 2 that's inside the cube root. How many times does 3 go into 3? This is the 3 I'm referring to. It goes into it 1 time, so I'm going to get a 3 out, just one of them. But this time 3 goes into 3 perfectly, so there's none left over. So I'm scratching that out to show myself there's no 3's left over. How many times does 3 go into 7? Well, that goes into it twice, so I'm actually going to get 5 to the second out. I'm going to get 2 5's out, so 5. I'm going to get 2 of them out. But there's 1 that's left over because 3 goes into that 2 times with 1 left over. And so on the cube root, I have left over a 2 to the first, which is just 2, a 5 to the first, which is just 5, and 5 times 2 is 10. And finally, I have to take care of all of this stuff. So I have to multiply all this stuff together. So first I do 5 squared, which is 25. Then I would personally do 2 times 3, which is 6. And then 6 times 25 would be 150 cube roots of 10. And that would be my simplified version of whatever massive number this cube root of it was. Did that make sense?
Yes.
Any questions on this? Now, the other reason I don't like the way they teach it in Algebra 1 is, what would happen if you have this? I forgot why. Doesn't matter. I'm just going to put it in there. Would their way that they taught you work when you have variables?
No.
No. Does my way work? Yes. This is an imaginary 2 because there was nothing written. Remember, if there's nothing written, it's understood to be a 2. It's kind of like in front of the x, there's a 1. If there's nothing written up here, there's a 1. Right? There's a bunch of imaginary stuff in math, and it's stuff we need to understand. So this is a 2. How many times does 2 go into 6? Goes into it 3 times. So I got x out 3 times. None left over. How many times does 2 go into 7? It goes into it 3 times, but this time with 1 left over. How many times does 2 go into 10? Goes into it 5 times. And then finally I have the square root of y only left over because this goes into it perfectly. And that would be my simplified version of that up there. Questions on that? Questions on that? All right, so that's the review from what I want you to know. That's how I taught Algebra 1 when I taught Algebra 1, how to deal with square roots. Because then, like, when we transition to this day, you know, we have 3 third roots, 4th roots, and 5th roots. It's not going to change anything. You're just saying how many times is 3 go into those, how many times is 4 go into those, how many times is 5. It's not going to change the process. Something else we need to realize from Algebra 1 is if I take a number and I square it, what can you guarantee me is going to happen? What kind of number can you guarantee is going to be over here?
A positive one?
A positive, or technically what? Or 0. But what will you never ever see here?
A negative number.
Because when you take a negative and you times it by another negative, those two negatives cancel each other out, giving me a positive, right? What happens when I have something to the 3rd power? What kind of numbers can I get?
Negative.
You can get positive numbers, you can get negative numbers, or you could get 0. What happens when I have x to the 4th power? What could I get?
Positive or 0?
Good. What happens when I have x to the 5th power? Ashton?
Positive 0. Hello?
Yeah, what? Keep
Oh,
going.
okay.
Keep going. What does it mean to raise something to the 5th power, Ashton? It means you're going to take the same number and you're going to multiply it by itself 5 times, right?
Mm-hmm.
Well, what happens if x is negative? These are going to pair up and make it a positive, right? These are going to pair up and make it a positive. This guy is going to kick it back to a negative. So if you have this, you could equal positive numbers, you could equal 0, but you could also equal negative. Because if you put a negative x in, these make positive, these make positive, then this makes negative. This is positive, that would make it negative. Do you follow me on that?
Yeah.
There's a pattern here. What if we had x to the 6th power? What would it be? Only positive or 0. If we have x to the 7th, it would be positive, negative, or 0. Now, the reason we're talking about this is because this relates to square roots. This relates to cube roots. This relates to 4. That can be underneath your square roots. What are the only types of numbers that could be under here? Are going to be numbers that are positive or 0. What cannot be under here? Negatives cannot be underneath there. Not imaginary they could be, but we're not. We're only talking about real numbers, so a negative can't be underneath there. What kind of numbers could be underneath a cube root? Positive, negative, or 0. What numbers could be under a 4th root? Only positive or 0. What numbers could be on a 5th root? Positive, negative, or 0. Are you guys following me here?
Yes.
So if I asked you for the square root of -4, what would you tell me? And we're talking about real numbers only. Your answer would be no real solution. If I asked you for the cube root of -8, you would find an answer here. Why? Because you are allowed to have a negative underneath. In fact, your answer would be -2. Why? Because -2 times -2 times -2, this kicks me to a 4, but then this kicks me to a -8. So this would be my answer. So we can have negatives under odds, but not negatives under evens. That is something we are supposed to recognize today. Does that make sense so far?
Yes. Can we do another one?
What part do you need help with? Is it?
When it's like positive to negative, like what we just did, what you went over. Can we do another example?
I mean, the thing that you need to know is if it's even, you can't have a negative underneath here. Why? Because when it's even, that means you have to have the same number, like it's gonna be like this. And what happens when they negative and negative? Positive, negative, negative, positive, negative, negative. In the evens, they'll always have a pair to kick back to positive. When you have an odd, you have one man out, right? So you have a pair here, you have a pair here, you have a pair here, but then you have this one guy, he's gonna make everything else become negative when you multiply. Do you understand that fact, Izzy?
Yeah.
So when I'm doing that, roots are the opposite. This means I'm going to have two numbers multiply to get this. Well, that means you'd have to have two numbers that when you multiply them would give you a negative, right? Because what's the square root of 25? The question I'm really asking is what number times itself twice is 25? That's the question I'm asking. Well, what number times itself twice is 25? the answer would be 5. Right? But if I asked you for the square root of negative 25, is there a number that I can multiply by itself? Heck no, because if you put in negative 5 times a negative 5, what happens with the negative and negative? They kick to a positive. There is no answer to this one. No real answer. It's imaginary, back when we did imaginaries at the beginning of the year. Does that help out, Izzy?
Yeah, that helps a lot. Thank you.
So when I have odds, right, like the square root of negative 8, I can do that one. It's negative 2. Why? Because I'm multiplying by an odd number of negatives. And what happens is these guys, by their powers combined, make positive. But then when I throw this guy in, it kicks it back to negative. But if I did 4th root of negative 16, I can't do that. Because a negative 2 times a negative 2 times a negative 2 times a negative 2, this would kick to positive, this would kick to positive, so this would be a positive 4 times a positive 4, which is equal to a positive 16, not a negative 16, so this wouldn't work. Isabella, does that make more sense now?
Yeah, that makes more sense. Thank you.
Now, the other thing that we need to think about is this. So this is just by fact. If someone asks you for the square root of 4, your answer is 2. But if someone says, what number times itself equals 4? Do you see in the original question, there's a square root in this one. In this original question, there is no square root. So when I go to do this, I put the square root sign in. So when I put the square root sign in, I must put a plus or minus sign. Why? Because the person asked me what number times itself equals 4. Well, 2 times 2 is 4. Check. But negative 2 times itself, negative 2, is also 4. And they wanted what number times itself. So I have to give them both answers. So when you put the square root sign in there, you must put the plus or minus. When the square root is already part of the problem, that's already there, you do not put this plus or minus. So if someone asks you, what's the square root of 16? Your answer is 4. If someone asks you, what number times itself is 16? Your answer is plus or minus 4. Does that make sense?
Yes.
Tricky question. What is my answer for this one?
Plus or minus 2.
Okay. I appreciate your effort, but I want you to think about your answer.
Would it just be positive 2?
Kelly, can you explain why it would only be positive 2 and not the plus or minus 2?
Because we want it to be positive. So if we did negative 2 times negative 2, that does make a negative 4. But then if we do
it's a positive 4. Yeah.
Positive, and then if we do another negative 2, it makes it negative.
Which is negative 8. Is that what I asked it to equal in the original? Janina, do you see that?
Yeah.
So guess when you only put the plus or minus sign? When your index, or when that power was even. So like if I asked you x to the 4th power equals 16, which means what number times itself 4 times is 16? Your answer would be plus or minus 2. Why? Because 2 times 2 times 2 times 2 is 16, and negative 2 times itself 4 times is also positive 16. But if I asked you x to the 5th power equals 32, your answer for this one is only positive 2, because negative 2 would actually give you a negative 32, which is not the answer. Or if they said negative 32, your answer would just be negative 2. And you can do this one because it's odd. If I gave you this one, you would say no solution because you can't get an even to a negative. So this all kind of works together, understanding this concept of positive and negatives and even and odd powers. How are we doing so far?
Good.
All right. I want to practice this because this is going to be the biggest part. So I want you to do this one on your own and tell me what you come up with. So I want the third root of Go ahead and try that one on your own. By the way, when you do your tree diagram, you want to use the biggest numbers in the beginning to break it down. You don't want to use like 2. That will take you forever. So you want to try to use the biggest numbers you can. That will make it go much faster. All right, this should definitely be one of the ones you want to make sure you know how to do before we leave today. You should be breaking down 1,000, or 12,000. First, I would break this down into 12 and 1,000. I would then break this down into 10 times 100. Break this down into 10 times 10. By the way, it doesn't matter how you break it down. Break this down into 3 times 4. Remember, you don't stop until everything is primed. 2 times 2, so that's done. 2 times 5, so these are done. 2 times 5, these are done. And 2 times 5, so these are done. And so I would rewrite all of this as, I do, because you see how much crap's over here, I would do smallest first. So I'd go 2, and then I'd start counting. 1, 2, 3, 4, 5. So that's 2 to the 5th times 3. I think there's only 1 3. And then times 5 to the 1, 2, 3 power. And write the variables: x to the 4th, y to the 3rd, z to the 7th. Does anyone have any questions on that? All right, now, how many times does 3 go into 5? That's how many 2's I'm going to get out. Well, 3 goes into 5 only once, so I get 1 2 out. But the problem is there's 2 2's that are left over inside, because 3 goes into 5 one time, but with 2 left over. There's a power of a 1 here. It's not written. I just understood that. How many times does 3 go into 1? It doesn't, so sorry, 3. You have to stay inside there. How many times does 3 go into 3? It goes into 1, so I get a 5 out. There's none left over. Now I'm moving on to my variables. 3 goes into 4 one time with 1 left over. 3 goes into 3 one time with none left over. And 3 goes into 7 2 times with 1 left over. And so I still have the cube root of 2 squared, which is 4. Multiply that out. 4 times 3 is 12. And then x, there's no y's, those were gone, and then z. And then finally, multiply this, or instead I'm just going to erase that. 2 times 5 is 10. So this would be my final 10. This would be my final complete answer. Be careful right here. Make sure that this z has the 2 and that this 3 belongs to this index. Just be careful with your handwriting, because it does get confusing if you mix that up. Kind of sucks. Does everybody understand what we just did there?
I understood it.
All right, we're just going to start something real quick just to show you this, and then today we'll be finished, and we'll finish the notes. I will put up homework probably in just a minute. Just please make sure you do as much as you can tonight. If it doesn't make full sense, wait till I finish the lesson tomorrow, because I'm only doing part of 5.1. But do as much as you can tonight. See if you can come up with some of this stuff. So here we go. This is called a power form, and I'm going to teach you today how to change from power form to radical form, which means that we're going to have the square root symbol, this symbol in there. So this right here, the denominator is always the index, so that's going to go right there. This number right here is always going to be the base number here, and this number right here is going to be the power of the base number. And then we would simplify it. By the way, the other way we could do this, and I'll show you a better example in a second, is we could actually rate this as the fourth power, or fourth root of 16, and then take that and raise it to the first. Here, we're doing this power first, then taking the fourth root. Here, we're doing the fourth root, then raising it to the power. Both of these will give you the same number. And if you simplify this, this would turn into, by the way, you don't need to see if this has, you don't need to try to do the tree factor first. Actually, what you should try to do first is see if 16 has a fourth root on its own, and it does, it's 2. So there's no reason, if you broke this down, by the way, it would do 4 times this, then 2 times 2, and then 2 times 2. So you'd end up with the fourth root up to the 4th power, which these would cancel, leaving you just a 2. But there's no reason to do that. Sometimes you just might want to pop in your calculator real quick. Does 16 have a 4th root? And if you do, it would go right to that. So check the calculator first, see if it has a nice pretty root first. And then if it doesn't, then you go to the tree factor. But like this one, 27 to the 2/3 power. What that really means is that means the 3rd root of 27 to the 2nd power. Personally, I would not write it like this, but that's because I've practiced this enough and I know that 27 actually has a nice pretty cubed root. So what I would do first is I would think of these are the same. I would see if 27 has a nice pretty cubed root. If it does, then I'm going to do this way. If it doesn't, then I have to do this way and simplify it, since like the way I did at the beginning of class. I'll show you one of those examples tomorrow. But like since 27 has a nice pretty cube root, which is 3, I can just take 3, that's the cube root of 27, and then square it, which is 9. And it doesn't take that much effort. Rather than taking 27 and squaring it, and then finding the cube root of that, I think this way is much faster. But you can only do this way if 27 has a nice pretty cube root. If it doesn't, you have to use this way. And like I said, I'll show you that tomorrow. But this is changing from power form to radical form, and just to make it to where we can make sure we understand this. If someone ever gave me this is what we call radical form, and they said, I want you to put that in power form, this is the base number, so it's 61. This is the numerator, 3. This is the denominator, 4. These two things are the same. So you can go from radical to power, or you can go from power back to radical. They are interchangeable. They are the same exact number. So we can, sometimes we want the radical form, sometimes we want power. That's what we're going to do throughout this chapter. We're going to switch back and forth between them. So other than that, that's it. And we will pick up on this tomorrow.